In the last couple of videos, we've been looking at generic trees. And up to this point, we've said that every single node in a tree can have an unlimited number of children underneath it. So for example, the root node in this tree has 3 children. And then this node right here of value 0 can have 3 children underneath that. We've also said several times that we can stick absolutely any data that we want to into any node of our tree. We're now going to start to look at another type of tree that is going to more closely validate or place more stringent requirements on not only the number of children that a node can have, but also the value that a child can have as well. So let's take a look at this new type of tree. So it's going to be called a binary search tree. With a binary search tree, every node can have at most 2 children. We usually refer to these 2 children by their position relative to the parent. So for example, for the root node, we have 1 node to the left and 1 node to the right. We would thus call the node over here on the left node, and the one over here the right node. Makes sense, right? Not that bad. Now, not only do we restrict the number of children that a binary search tree node can have, but we also start to restrict or start to validate the value of every node in the structure. In this particular case right here, you can very quickly notice that every single value to the left of a parent node seems to have a value less than the parent. So for example, the root node in this case has a value of 10, and then the value to the left has a value of 0. The same is true of this node as well. So to the left, we have -1, which is less than 0, and to the right, we have a value of 5, which is greater than 0. And then even down here with, say, 20. We have 20 in the parent. The left node has a value of 17, which is less than 20. And the right node has a value of 99, which is greater than 20. So we can really come up with a diagram that looks like this for any given node in our structure. So this represents a node right here. Rather than referring to the children of a node as a big array called children, because we only have at most 2 child nodes, we usually assign them to properties called left and right, which corresponds to the left node and the right node, of course. We also place these validation requirements on the values inside of those left and right nodes as well. So the value of this parent node, this current node that we're looking at right here, must be greater than the value of the left node's value. And then the value for the right node must be greater than the current node. With binary search trees, you'll frequently call the value or the data stored within the node other types of terms than what we've been using as well. So you'll sometimes see the data stored within the node itself. You'll frequently see it referred to as a key. You might see it referred to as a value, but for the purposes of this course, we're going to continue to call it data just to stay consistent. Now, one of the big challenges around binary search trees, or one of the questions that you can probably be expected to most frequently have to answer in an interview setting, is exactly how to add new nodes into an existing binary search tree. So let's say, for example, we have the given tree right here, and then we call add on the root node all the way up top, and we want to add in a new value of -20. It would then be up to you and me to write some code to figure out exactly how to take this new value of -20 right here and somehow add it into an appropriate location within the tree. So the general algorithm for this is pretty straightforward, at least from a verbal perspective, like talking through it. So to add in a value of -20, we would start off at the root node and we would say, is -20 less than 10? Yes, it is. So we're going to go to the left-hand side. We then say, is -20 less than 0? Again, yes it is, so we move to the left-hand side. And then we say, is -20 less than -1? And again, yes it is. So we would allocate -20 right here. Now the last thing I want to mention about binary search trees is the actual naming of the tree as well. So we are going to be talking about binary search trees. Now it's specifically the term search in there that places the requirement on the values to the left and right of the parent node. We can just as easily, and this is a thing in the computer science world as well, so this is another completely valid data structure, we could also have simply a binary tree. A binary tree is a normal tree that just has 2 nodes underneath each parent. So with a binary tree, we no longer have the requirement of making sure that the values on the left are less than the parent value and that the values on the right are greater than the parent value. So for example, if we replaced 5 right here with like 999, we would no longer have a valid binary search tree, but we would have a valid binary tree because every node in here has at most 2 children. So that's just one thing to keep in mind. Now in an interview setting, one thing that you'll want to do very frequently whenever you think you're being asked about binary search trees is to really try to get an answer to the question very quickly whether or not you are working with a binary search tree. Very commonly, your interviewer might expect you to kind of deduce whether or not you're working with a binary search tree or not. And also some types of algorithms will behave slightly differently whether you have a binary search tree or just a normal binary tree. One other common interview question that we might see as well is to be asked to validate a binary search tree. So maybe you are given a tree that looks like this right here, and you have to run some code on it and validate whether or not it is well formed. In this particular case, where every node has 2 children, and every node to the left of its parent is less than the value of the parent, and every node to the right is greater than the value of the parent, in this case, yes, we have a valid binary search tree. But if you were given a tree that looked like this, where there was some value out of place, you would then be expected to somehow find this mistake right here and say, no, it looks like this is not a valid binary search tree. Okay, so that's a little bit on binary search trees. Again, it all comes really down to understanding how to insert new nodes into a tree. So we're going to continue in the next video where we're going to start working on our own implementation of a binary search tree. And it's really going to focus on our ability to add in new data or new records to it. So quick break, and we'll continue with that in the next video.